Nvidia's own finance chief just told investors something that should scare every tech company on Earth. Zero. That's how many of their most advanced AI chips are shipping into China this year. Not fewer. Not reduced. Zero. A $50 billion market walked out the door, and it didn't collapse. It built its own replacement instead. This is the story of how one banned company built a chip good enough to make Silicon Valley nervous, and why the whole world is now forced to pick a side. In 1987, a man named Ren Zhengfei started a small trading company in Shenzhen with almost nothing. He grew up poor, one of 7 kids in a family that didn't always have enough food. Before he built anything, he worked as a military engineer, learning how to solve problems with barely any resources. He didn't start his company because he had a big dream. He started it to feed his family. That company was Huawei. For years, Huawei stayed quiet. They built phone networks in places bigger companies ignored. Slowly, they moved into smartphones, and by 2019, they had become the second biggest phone maker on the planet, right behind Apple, selling in over 170 countries. Most people in the West had never even heard of them. Then the United States government called Huawei a national security threat. Washington cut them off from American chips and American software. Allies were pressured to do the same. A year later, the world's most important chip factory, TSMC in Taiwan, stopped supplying them completely. Overnight, a company that had just beaten Apple in phone sales could not get the parts to build a single phone. Picture a busy restaurant that suddenly can't buy a stove or a fridge, but the owner is still told to serve customers. That was Huawei in 2020. Suppliers who had worked with them for years cut ties in days. Most analysts thought this was the end. So Huawei started rebuilding from scratch. They redesigned thousands of circuit boards. They replaced over 13,000 banned parts with things they designed themselves. They built their own operating system after losing Google's software. Every door that closed, they tried to build a new one. And remember that 0 number from the start of this story. This rebuild is exactly what made that 0 possible. Inside Huawei sits a chip design team called HiSilicon, founded back in 2004 when nobody thought it would matter much. After the sanctions hit, this small team became the center of Huawei's survival plan. Their biggest project was a line of AI chips called Ascend. Think of an AI chip like a car engine. The bigger and more efficient it is, the more work it can do at once, and in AI, that work means training massive systems that power chatbots and self-driving software. For years, Nvidia built the best engines on the planet, and almost nobody came close. Huawei's answer was the Ascend 910C. By 2025, they were struggling to make enough of them fast enough. Bloomberg reported Huawei planned to roughly double production in 2026, aiming for around 600,000 of these chips, with total output across the whole Ascend line climbing as high as 1.6 million units. That's not a lab project anymore. That's a full assembly line running around the clock. But there was a massive wall in front of them. Designing a chip is one thing, manufacturing it is another. The most advanced chip factories use a machine called an UV lithography system, so precise it can trace patterns smaller than a human hair. Only one company on Earth makes these machines, a Dutch company called ASML, and each one costs over $200 million. The United States blocked ASML from selling its newest machines to China. Without that tool, almost every expert assumed China simply could not build advanced chips. It would be like trying to build a skyscraper with only hand tools. China's biggest chip factory, SMIC, refused to accept that. Instead of the newest machines, their engineers used older equipment they were still allowed to buy, called deep ultraviolet lithography. They ran the same silicon wafer through the machine multiple times, using a technique called multiple patterning. Picture tracing over the same drawing several times with a slightly different stencil each pass, adding a little more detail each time. It sounds simple, but it's brutally hard. One tiny misalignment ruins the whole chip. It's slower, more expensive, and the yield is far lower than top factories get. Industry estimates put SMIC's yield somewhere between 15 and 40%, while the best factories in Taiwan and South Korea get well over 90%. That means over half the chips from some batches end up in the trash, in a normal market that would kill the whole plan. China didn't treat this like a normal market. By mid-2025, SMIC had used this method to produce working 5-nanometer chips for Huawei, without a single UV machine involved. A former TSMC vice president told Bloomberg it was simply not possible for the United States to fully stop China from improving its chip technology. Push a country hard enough, he said, and they find a way. In April 2026, Huawei unveiled the Ascend 950 PR at an event in Shenzhen packed with executives from China's biggest tech companies. On paper, it delivers roughly 1.5 petaflops of processing power, meaning it can do 1 quadrillion calculations every second. And it carries over 100 gigabytes of high-speed memory. That puts it in the same conversation as some of Nvidia's best hardware. That was enough for China's biggest companies. Alibaba and Tencent placed major orders. ByteDance alone committed over $5.5 billion to Huawei chips for its data centers. By some estimates, Huawei's Ascend line is on track to capture roughly 60% of the entire AI chip market inside China by the end of 2026, with revenue projected past $12 billion.
A team of engineers in China just made a small stack of chips beat a full-size graphics card by 149 times, and they did it using light instead of wires. This is not a rumor or a marketing claim. It is a peer-reviewed result out of Peking University, and it exposes a weakness in every AI chip built today. The story is not about China replacing Nvidia. It is about something far more important hiding underneath that headline number. Every AI chip sold today is judged by one number: teraflops. That number tells you how fast a chip can do math under perfect conditions. It does not tell you how much time that chip spends doing nothing, just waiting for data to arrive. This waiting is called the memory wall, and researchers say it is the biggest hidden problem in modern computing. A graphics card can have thousands of cores ready to work, but if the data cannot reach those cores fast enough, most of that power sits idle. The team at Peking University decided to attack this waiting problem directly instead of building a bigger chip. They took a neural network with 5 layers and split it across 5 separate FPGA chips. An FPGA is a chip that can be rewired for one specific job instead of running general code like a normal processor. Each FPGA was permanently assigned one layer of the network. The first chip only ever handled layer 1, the second chip only ever handled layer 2, and so on through all 5 boards. Instead of connecting these chips with normal copper wires, the team connected them with light. Each FPGA got its own silicon photonic transceiver, a small device that turns electrical signals into pulses of light and back again. Each transceiver could move data at 400 gigabits per second. The light traveled using 4 different wavelengths at 1270, 1290, 1310, and 1330 nanometers, all packed onto the same fiber at once. These light signals pass through a 16 by 6 optical switch, a piece of hardware that can send light from any input to any output without slowing down or losing signal. Here is why light mattered so much. A normal network switch has to check, hold, and schedule every packet of data before sending it forward. That takes time. An optical switch skips almost all of that. It is closer to a clear path for light to travel straight through. This let one chip finish its part of the work and pass the result directly to the next chip almost instantly, with barely any delay. Think about a factory line building a toy in 5 steps. If one worker does all 5 steps alone, the next toy cannot start until the first one is finished. But if you split the steps across 5 workers, and each one hands off the toy the moment their step is done, all 5 workers stay busy at the same time. Finished toys start coming out one after another with no gaps. This is exactly what happened inside the optical chip system. Now here comes the number that shocked people. The team tested this system on a real task, cleaning noise out of small clothing images from a dataset called Fashionist. Each image was only 32 by 32 pixels. They ran 1,000 images through the system in batches of 10. The full 5P Gaia pipeline finished the entire job in 105.16 microseconds. To put that in perspective, a microsecond is 1/1,000,000th of a second. Based on the theoretical limit of the hardware, a perfect version of this system would have needed about 99.6 microseconds. That means the real system hit close to 94.7% compute utilization, an extremely high number in a field where losing 30 or 40% of performance to overhead is considered normal. Then they ran the exact same task on a commercial GPU with 372 CUDA cores and a theoretical peak of 16.96 teraflops. On paper, that GPU had more than 8 times the raw compute power of the 5FPGA system, which only reached 1.969 teraflops, but the GPU took 15.643 milliseconds to finish the same job. Compare that to 105 microseconds on the Lightlink system, and the difference comes out to almost exactly 149 times faster. A system with roughly 11.6% of the GPU's theoretical power beat it by nearly 150 times. That is the number that spread everywhere, but the real story is what caused it. The GPU lost because of overhead, not weak math.
Inside a secured facility in Shenzhen, something impossible just happened. Huawei, the company written off by sanctions, confirmed testing of a homegrown UV lithography machine in early 2025. The machine fills an entire factory floor and generates the exact 13.5 nanometer wavelength needed to etch 3 nanometer chips. When ASML, the Dutch monopoly holder, heard the news in March 2025, their stock dropped 7% in a single day. The experts who said this would take 15 years are now scrambling to explain how China did it in just 5. Let's be clear about what we're talking about. Extreme ultraviolet lithography is not just another manufacturing tool. Each ASML machine costs over $350 million, weighs more than 180 tons, contains 100,000 precision parts, and took 20 years to perfect. These machines use light with a wavelength measuring just 13.5 nanometers to print circuits 30,000 times thinner than a human hair. Without UV, making chips smaller than 7 nanometers is essentially impossible. ASML was the only company on Earth that could build these machines. Until now. Back in 2019, the Trump administration hit Huawei with sanctions that cut them off from American technology. ASML, under intense pressure from Washington, stopped shipping UV machines to China. Huawei's manufacturing partner, SMIC or Semiconductor Manufacturing International Corporation, was stuck using older Dove technology that maxes out at 7 nanometers. Western analysts were unanimous. Without UV access, China's chip dreams were finished. ASML's CEO said in December 2024 that China was still 10 to 15 years behind. That timeline just collapsed. China didn't try to copy ASML. They invented something completely different. Instead of ASML's laser-produced plasma that fires 50,000 pulses per second at microscopic tin droplets, Huawei developed laser-induced discharge plasma, or LDP technology. The method is simpler. Vaporize tin between electrodes, zap it with high-voltage electrical discharge, and you get plasma emitting the exact same 13.5 nanometer wavelength. But here's the critical part. It's cheaper, more compact, and bypasses hundreds of ASML patents. On January 3, 2025, Harbin Institute of Technology officially announced their breakthrough. Professor Zhao Yongpeng's team successfully developed an UV light source producing stable 13.5 nanometer radiation. Their discharge plasma extreme ultraviolet lithography light source project won first prize at the Heilongjiang Province Science and Technology Innovation Competition. The system achieved power levels between 100 and 150 watts by mid-2025. The technical specs are remarkable. A research team led by Lin Nan, a former ASML engineer now at Beihang University, published results showing a conversion efficiency of 3.42%. That might sound low, but ASML's research arm Arcanel only achieved 3.2% in comparable experiments back in 2019. These aren't wild claims. The paper was peer-reviewed and published in March 2025 by Chinese Laser Press. This is a coordinated national effort. Harbin Institute of Technology developed the light source. Chengchun Institute of Optics created high-precision reflective mirrors with accuracy down to 0.2 nanometers, reportedly surpassing lenses jointly developed by ASML and Germany's Zeiss. Shanghai Microelectronics Equipment Group, known as SMIC, handles overall integration. Huawei and state-backed firm SiCarrier coordinate more than 3,000 researchers across lithography, deposition, and etching equipment development. The Chinese government committed $37 billion specifically for UV lithography development, with additional investments in semiconductor self-sufficiency totaling over $150 billion through 2025.